European Groundwater Geochemistry. On this slide, you see the contents of the seminar. I'm not going to go through them. You can study them at your leisure later on. The Forex Geochemical Atlas of Europe collected samples of stream water, stream sediment, floodplain sediment, topsoil, and subsoil. What is missing? Groundwater. Water is the most valuable natural resource for our quality of life. As you can see on this slide, approximately 96% of the water on Earth is salty and is in the oceans and seas. Approximately 3% is in glaciers and polar ice, and slightly more than 1% is fresh and available for use. Nearly 70% of the world's fresh water is locked in ice. Most of the remaining is in aquifers that we are draining much more rapidly than the natural recharge rate. 2/3 of our water is used in agriculture to grow our food. With 83 million more people on Earth each year, water demand will keep going up unless we change the ways we use it. This is a report from National Geographic in 2010. As we can see here, in Haskell County, Kansas, 1,100 producing wells tap the groundwater, and if this continues, there will be a problem in the near future. According to President Seaver way back in 2002, human activities constitute a massive interference in the operations of the natural hydrological cycle. Some of these interferences are: evaporation is increased by the use of irrigation waters in dry areas. Runoff patterns are altered where water is diverted from one region to another. Paving that covers the Earth's surface with motorways, car parks, and buildings decreases infiltration. Human contribution to global and local warming can lead to melting of glacial ice and changes in the balance of water in other reservoirs. As threats of water shortage loom, water usage enters the arena of public policy debate. 1 out of 8 people lacks access to clean water. 3.3 million people die each year from water-related health problems. Washing hands with soap can reduce diarrheal disease by 45%. An eradication campaign that includes a simple water filter has reduced the number of guinea worm cases by 99.9% since 1986. You see what the shortage of water can do. This is a village in India, and where people are trying to get their water from just one well. Here we see a contradiction. An area in Mumbai where we have a water park with plenty of water, and other areas such as Palestine, India, and Kenya with shortage of water. These women travel every day for 5 hours for their daily water. In this slide, we see the chemical element prevalence in the human body. As you can see, 74.5% of our body is made of oxygen and hydrogen. Milk, egg, vegetables, and human blood consist of 70 to 90% of water. The body of this baby in the swimming pool is 75% water. Based on the title of the first United Nations World Water Development Report, Water for People, Water for Life, the General Assembly of the United Nations decided to proclaim in its resolution the period from 2005 to 2015 the International Decade for Action Water for Life, which commenced on World Water Day, 22nd of March 2005, and is celebrated on the 22nd of March every year. The resolution states that the main goal of the decade should be a greater focus on water-related issues at all levels and on the implementation of water-related programs in order to achieve internationally agreed upon water-related goals contained in Agenda 21, the United Nations Millennium Development Goals, and the Johannesburg Plan of Implementation. Words, words, words. Question: is this enough? Young Europeans discussed sustainable development in Athens on the 10th and 11th of May 2011. Their worries and concerns 13 years ago, ensuring our survival, water and food. We are talking about a water crisis. 1.1 billion people in developing countries have inadequate access and 2.6 billion people lack basic sanitation. About 1.4 million children will die each year from lack of access to safe drinking water and adequate sanitation. What are the water management methods that could ensure sustainable access to water and food for everyone? What are the strategies to deal with naturally occurring or anthropogenic water-related hazards? Hazards can result from too much water, floods, erosion, landslides, and so on, or too little, droughts, desertification, and loss of wetlands or habitat, and from the effects of chemical and biological pollution on water quality. Question: has anything changed during the past 13 years? With an ever-growing world population and drastic global climatic changes, groundwater will become a valuable resource for our well-being. Clean and safe water is important for our health. And according to Ritchie et al., 1 in 4 people in the world do not have access to safe drinking water. This is a major health risk. Unsafe water is responsible for more than 1 million deaths each year. And we can see on the map the areas where there is a water shortage. In this slide, we see deaths by risk factor for 2019 statistics. Unsafe water source, as we can see, is the 14th risk factor, and no access to a hand washing facility is the 20th risk factor. In this map, we see the areas where people not using safe drinking water facilities. Following the short introduction, we come here to the main part of my talk, the development of the project idea that I'm going to show you the results, the problems, and their solution. The European Environmental Agency contacted in 2007 the EuroGeoSurveys Geochemistry Expert Group whether there was a harmonized geochemical dataset for groundwater similar to the stream water geochemical dataset produced during the multi-sample media project of the Geochemical Atlas of Europe. Of course, the answer was negative. However, there were discussions among the members of EGS-GEG if such a project was possible to be carried out cost-effectively. Groundwater, it is a difficult medium to sample. Contamination issues, as we see in this diagram. It is difficult to map, 3D regional distribution, aquifers. It has a high local variation. Conclusion: groundwater is a medium that is impossible to sample systematically and analyze at a reasonable cost. In this slide, we see a simplified diagram of the hydrogeological cycle of an idealized stratabound sedimentary aquifer. A limestone sandwiched between layers of low permeability sandstone. Rainfall seeps into the outcrop area of the limestone to form groundwater. The groundwater dissolves calcite in the limestone to result in a fresh, cool, typical calcium bicarbonate groundwater. This type of water would be favored by producers of bottled spring water in many Western European nations. As the water flows down deep through the aquifer, it becomes warmer and increasingly mineralized. It may even mix with relict silent groundwater in the deepest parts of the aquifer to form a true mineral water in the classic tradition. The German Federal Institute for Geosciences and Natural Resources offered to analyze free of charge all collected groundwater samples from all European countries. There was, however, an almost impossible problem. No funds were available to carry out systematic sampling of groundwater in Europe. The main reason was that the European Geological Surveys were committed at the time to planning the sampling of agricultural and grazeland soil, the GEMAS project. Manfred Birke from the German Federal Institute for Geosciences and Natural Resources came up with the idea that bottled mineral water can be used as a proxy for the geochemistry of groundwater. According to Manfred's experience, the geochemistry of bottled mineral water can be used as a proxy for that of groundwater. In Europe, there are more than 1,900 registered bottled water brands. Therefore, bottled groundwater can be bought readily sampled at the European scale from supermarkets. Manfred's idea was considered absurd and that the EuroGeoSurveys Geochemistry Expert Group would be criticized for carrying out such an unconventional project. Manfred Birke insisted and supported his proposal with reference to European Commission legislation. In Europe, there are three categories of bottled water. Natural mineral water. It is drinking water of underground origin with a stable chemical composition and is bottled at source, spring, well, borehole. It is not subjected to any treatment and differs from common drinking water by its mineral content, trace elements, or other constituents. Spring water. It is drinking water of underground origin and is bottled at source. It is not subject to any treatment. It is not required to have a stable chemical composition. Its physicochemical characteristics parameters must satisfy the standards of drinking water for human consumption. Table water. It is bottled water for human consumption. Its physicochemical characteristics parameters satisfy those of common drinking water. It can even be a normal tap water or treated and disinfected river water. And this is not suitable for the project. During the discussion, there were issues considered when using bottled mineral water as a proxy for groundwater geochemistry. Bottled mineral water may come from non-representative, quite special and unusual aquifers, can be contaminated from well and bottle installations, and can be contaminated from the bottle material itself. Bottled table water is treated prior to bottling, filtered, carbonated, de-iron, etc. Hence, bottled table water is unsuitable for sampling. Decision time. Do we go ahead with the project? Yes or no? It is noted that most members of the EuroGeoSurveys Geochemistry Expert Group are applied geochemists with experience in mineral exploration, where they learn to sample and measure systematically any natural medium to meet project objectives in a cost-effective manner. Manfred's proposal was discussed, and although it was met with considerable skepticism, the explorationists among the group decided that it was worth a try, since the cost of sampling was minimal. That is just the cost of purchasing the bottled mineral water from supermarkets and of posting the samples to Germany. Sampling of bottled mineral water from supermarkets. Instructions were sent to all members of the EuroGeoSurveys Geochemistry Expert Group, as well as to friends and colleagues traveling to European countries, to purchase from supermarkets as many different bottled mineral water brands as possible. In case the same bottled water was available with and without gas, both varieties were purchased. If bottled water was marketed in different bottle types, for example glass and PET, or in bottles of different color, all varieties were bought whenever possible. To keep shipping costs down, 0.5-liter bottles were preferentially bought. However, if a brand was exclusively marketed in larger capacity containers of 1, 1.5 or even 5 liters were purchased. Before shipping to Germany, the analytical results recorded on bottle labels were transferred to an Excel worksheet together with other pertinent information. Over 85 scientists in 40 European countries collected the project water samples. The sampling or purchase of bottled mineral water from supermarkets started in November 2007 and was completed by April 2008. Duplicate bottled mineral water samples of the same brand were purchased from different supermarkets. Bottled mineral water was not purchased from kiosks. The reason is that bottled mineral water is exposed to the ambient temperature, as we see here. In total, 1,785 samples of bottled mineral water were purchased from supermarkets all over Europe. representing 1,247 boreholes, wells at 884 unique locations. Upon arriving in Germany, all bottled mineral water samples were stored in refrigerators until their analysis. So Manfred Birke had to buy many refrigerators to store the 1,785 bottles of mineral water. To obtain a fully harmonized geochemical dataset, all bottled mineral water samples were analyzed for 72 parameters in just one laboratory, the BGR laboratory in Germany. In this slide, we see the analytical program of the Atlas of European Groundwater Geochemistry, and as you can see, some elements were measured by different methods. Here we see the Excel sheet of the analytical results received from the laboratory. The quality of results was first checked. Data processing, basic statistics followed, plotting of maps, interpretation, report writing, the atlas books, and publications. The instrument detection limit was estimated at 3 times the standard deviation of sample blank determinations. The reported detection limit was calculated at 10 times the standard deviation of sample blanks. The conservative RDL was used as the cutoff value for all statistical graphics and tables, as well as for producing the distribution maps. The duplicate analyses were also used to estimate the practical detection limit. In this case, the PDL was used for the verification of the reported detection limit. And as we can see here, in some cases, the PDL values indicate that if ancestral values were provided, a much lower detection limit could have been estimated. A very strict quality control program was installed. Analysis of international reference samples to document the trueness of analytical results. Frequent analysis of an in-house project standard, MINWAS, to check the accuracy of determined parameters. Frequent analysis of blank samples to detect any contamination issues and to estimate reliable detection limits. Frequent analysis of sample duplicates to determine the precision of measurements. Comparison of analytical results of this study with those displayed on bottle labels. Determination of a few parameters by ICP-MS and ICP-AES and mercury by ICP-MS and the AFS. Checking bottled mineral water samples with unusually high results for important parameters by buying another bottle and repeating the analysis. The international sample SLRS-4 was analyzed 103 times. The low 45 standards for trace elements TM 26.3, 27.2, 28.2, 28.3 were randomly analyzed from 25 to 91 times. The in-house laboratory reference sample MINWAS was randomly analyzed 261 times, and the blank samples of the ionized water and acid were randomly analyzed 10 to 12 times. The only problems that were detected during the study of quality control results concerned the reproducibility of hafnium, niobium, tin, tantalum, and tungsten at low concentrations. Consequently, the results of these elements up to concentrations 10 times their detection limit should be considered with some caution. However, the results of reference samples at higher concentrations show that these results are reliable. In this slide and the next few, we will see Thomson and Howard precision charts. I strongly recommend that you use the Thomson and Howard precision charts to plot the results of your duplicate analysis. They are very simple to plot. On the x-axis, you plot the mean value, and on the y-axis, the absolute differences of your duplicate analysis results. And here we see the results that are acceptable of copper, because most of the results fall below the control line of the 90th percentile for the 10% precision. And here we see unacceptable results for bismuth because most of the results fall above it. On this slide we see the results of hafnium, which is poor results, as you can see, because they fall above the 90th percentile control line or 10% precision. And of course it's quite obvious, you see most of them are very low results. We see similar problems with the niobium and tin duplicate results, and also the tantalum and tungsten duplicate results show a poor precision. This is the publication. It was published in 2010, and all the analytical results are on the DVD. We also have many papers published in a special publication of the German Geochemical Exploration called Mineral Waters of Europe. Here we see the colleagues that have worked in different parts of the publication. This is a slide showing most of the people that work on the publication at a meeting we had in Athens in 2010. The distribution maps were prepared using the variable size or growing dots method. In the publication, in the printed atlas, we have black dots, and in this presentation, I have replotted the maps with the color dots. To be able to get a more objective impression of whether there exist regional scale differences in the observed element concentration and non variation in Europe, the dataset was subdivided into 4 quadrants: northwestern, northeastern, southwestern, and southeastern. And here we see the box plots. Here we see the atlas pages. On the right-hand side is a distribution map, the statistics, and on the left-hand side is the text with interpretation. Here we see an enlarged part of the statistics, the different diagrams, and also where there is a drinking water standard, it is mentioned. Here we see the distribution map of arsenic, and as we see, the anomalous samples occur near sulfide mineralization zones, and also the alkalic volcanic provinces in Italy. On the right-hand side, there is a mineralization map, and so you can study at your leisure the relationship between the two. Here we see the chromium distribution map with anomalous samples occurring in areas with ophiolites, mafic and ultramafic rocks. And on the right-hand side, we see the distribution of ophiolites. The nickel distribution map showing again anomalous samples occurring in areas with ophiolites. The vanadium distribution map, anomalous samples occur in the vicinity of active volcanic centers and basaltic rocks. The lithium distribution map, where the anomalous samples occur in areas with hercynial granites, Jurassic and Triassic sediments in Germany, and deep source water wells, for example in the Carpathian mountain chain and the Balkans. The potassium distribution map, which has similar patterns to those of lithium. The cesium distribution map, again, the distribution patterns are similar to those of lithium and potassium. The rubidium distribution map, again, the patterns are similar to those of lithium, potassium, and cesium. Here we see the fluoride distribution map. Most mineral waters show high fluoride values in northeastern Europe, where many true mineral waters are bottled. Several wells abstracting waters in area underlain by young granites exhibit unusually high fluoride concentrations, as we see in Portugal and the Massif Central in France. In Italy, water extracted from wells in areas with tertiary alkaline volcanics show elevated fluoride concentrations. In Bulgaria, the high fluoride concentrations are possibly due to Paleozoic granites and fluoride mineralization, for example, the Milhalkovo deposits. The highest values of 10.7 milligrams per liter of fluoride was reported from a well from Georgia, and it was marked as medicinal water. Many of the anomalous wells can be traced to deep fault zones. And regarding the standard, only one sample exceeds the 5 milligram per liter of fluoride. The nitrate distribution map, samples from southern and eastern Europe and the British Islands have the highest nitrate concentrations. The spatial distribution cannot be linked to known geological features, nor would such a correlation be expected, as nitrate is typically released by surface and atmospheric processes. The highest value of 995 milligrams per liter was reported in a bottled mineral water from the Czech Republic. The elevated nitrate concentrations are ascribed to human activities. And with respect with the drinking water standards of 50 milligrams per liter of nitrate, only 2 bottled mineral water samples have values higher than this limit. The chloride distribution map, most of the anomalously high chloride wells can be traced to deep formation waters, although chlorine derived from hydrothermal and volcanic activity may also be a source of elevated chloride. The highest value of 3,627 milligrams per liter of chloride was reported from a Slovakian well. The highest value in Norway is influenced by saline pore waters from marine clays. In this case, 68 samples exceed the 250 milligrams per liter limit. The iodine distribution map, similar to chloride, most of the anomalously high iodine can be traced to deep formation waters. The highest value of 4,030 milligrams per liter iodine was reported from the same Slovakian well. The highest value in Norway is influenced by saline pore waters from marine clays. It is stressed that iodine is a difficult element to analyze with ICP-MS, and due to its importance for human health, special care was taken to obtain reliable results. On this slide, we see the Duro diagram for the bottled mineral water data. It is a complicated diagram which you can study at your leisure. Here I've just pointed at the most significant features. The diagram is based on milliequivalent fractions of the major cations and anions. The size of the symbol is related to the total dissolved solutes on the basis of electrical conductivity. And we see the more normal groundwaters of calcium bicarbonate type derived from calcite hydrolysis. They plot in the top left corner. The more evolved granitic groundwaters characterized by prolonged aluminosilicate weathering might be of sodium bicarbonate type and plot at the top right corner. The dilute recharged waters possessing a weak signature of marine salts in coastal areas will plot as small dots low electrical conductivity in the lower right field, they will be termed as low ionic strength sodium chloride water type, and the deep saline brines will most likely be of sodium chloride composition and plot as large diameter dots, high electrical conductivity near the bottom right corner of the diagram. Here we see a ternary diagram of bicarbonate, chlorine plus nitrate and sulfate. And you can see most of the bottled mineral water samples are carbonate rich, followed by sulfate rich, and chloride nitrate, and mixed water. On this slide we see a ternary diagram of calcium, sodium plus potassium, and magnesium. And most of the bottled mineral water samples are calcium rich, followed by potassium sodium rich, mixed water, and magnesium rich water. On this slide we see the Gegenbach potassium magnesium sodium triangle, which verifies the extent to which water rock equilibrium has been attained. It combines the sodium, potassium, and sodium magnesium geothermometers. Most of the European mineral water samples are of shallow origin, as we can see here. A few samples are sourced from deeper well boreholes, reaching a temperature of up to 130 degrees Celsius. This slide and the next few, they show the leaching of elements from bottled materials. On this slide we see the scattered diagrams showing the dependence of pH in relation to total alkalinity and pH in relation to lead, according to bottle type, glass and PET, and whether they are still in black or carbonated water in gray. And as we can see, there is separation. Here we see the dependence of pH in relation to antimony and antimony in relation to lead, according again to bottle type, glass and PET, and whether still or carbonated water. And again we see distinct separations. On this slide we compare the antimony concentrations in the same type of bottled mineral water sold in glass and PET. And as we can see on the XY plot, the antimony concentrations are higher in the PET, and similar in the box plot comparison, we see that the PET bottles have higher antimony concentrations compared to glass. Here we see the chromium statistical distribution between clear and green glass bottles, and as we can see here, there are higher concentrations of chromium in the green bottles, and similarly we see this in the box plots comparison. Higher concentrations in the green bottles compared to the clear bottles. On this slide we compare the concentrations of lead and thorium in glass and PET bottles, and as we see, the glass affects more the concentrations of lead and thorium, and similarly from all the other plots we have plotted, the same happens with cerium, aluminium, zirconium, titanium, hafnium, and lanthanum. We have used measurement uncertainty to assess compliance of bottled mineral water with the drinking water standards, and the method is from Ramsey, 1998. We use the balanced ANOVA design, and you can read all the details in this publication. Here you see the philosophy of the assessment of compliance. I'm not going to go into detail. You can read the notes at your leisure, and also the paper. And if you don't have access to it, please send me a message and I will send it to you. Here we see a summary table of the elements that exceed the minimum EU statutory water standard with respect to aluminium, arsenic, boron, barium, iron, manganese, nickel, and selenium. On this slide, the next few, we'll see a comparison of results among the 4 data sets of water samples: the European bottled mineral water, the European stream water, the European tap water, and Norwegian groundwater. On this slide, we see the comparison of arsenic and vanadium. And most elements, as you see, show a surprising comparable distribution in all 4 data sets. Here we see the cesium and lithium comparison plots. And as we have seen with the other plots, some elements, for example, silver, boron, beryllium, bromine, chlorine, cesium, fluorine, germanium, iodine, potassium, lithium, sodium, rubidium, strontium, tellurium, thallium, and zirconium, show a mineral water specific enrichment +1 to 2 orders of magnitude variation. And these are from deep sources, brines, and hydrothermal water. The comparison plots of copper and lead. Here we see definite indications that the European tap water and Norwegian groundwater are contaminated by well installations and water piping over the whole concentration range. Here we see a very interesting plot of uranium in bottled mineral water, and we see a sudden drop of values on 10 micrograms of uranium per liter. Now, the World Health Organization proposed a guideline value of 15 micrograms of uranium per liter, and it appears that the bottling companies are observing this limit. Here we see a comparison plot of the 4 data sets and the number of samples that exceeds the 15 micrograms per liter of uranium, which is the guideline value. We have 12 bottled mineral waters, 5 tap waters, 100 Norwegian groundwaters, and 2 European stream waters exceeding this value. On this slide, we see a comparison of the analytical data of the EuroGeoSurvey study with those displayed on bottled mineral water labels, which show a fairly good linear correlation. And this satisfies the legislative condition of stable chemical composition. Conclusions. Bottled materials contaminate bottled mineral water. Glass contaminates water with respect to these elements, and also some glass bottles contaminate water with antimony. Green glass contaminates bottled water with chromium, iron, and zirconium. Hence, the PET bottle results were used in the statistical data processing and map plotting, since the only problem is contamination of bottled mineral water by antimony. Consequently, the antimony distribution map was not plotted. Some brands of natural bottled mineral water are enriched in this set of elements and are clearly not representative of normal shallow groundwater, and the high values are typical of mineral water from deep aquifers. For most elements, the bottled mineral water analytical data set provides a realistic picture of their median value and variation in groundwater at the European level. Natural variation is enormous for most elements, usually 3 to 5, and for a few up to 7 orders of magnitude were observed. When discussing water quality, natural variation must be documented first. The present focus on pollution, contamination is misleading given the observed high geochemical background. It may be necessary to study more seriously the problems that are related to the deficiency of elements in groundwater, since water is an important source of elements such as fluorine, iodine, selenium, and barium. Geological characteristics which are visible on the geochemical maps include ophiolites with respect to chromium, nickel, and vanadium, alkaline volcanics and generally areas of active volcanicity with respect to these elements, Hercynian granites with respect to all these elements, deep structures with respect to strontium, deep sedimentary basins with respect to this set of elements. Thus, geology, or the rocks that the water is in contact with, is one of the key factors influencing the observed element concentrations in the bottled mineral water. Other significant factors are precipitation and proximity to the sea. Using bottled mineral water as a proxy for groundwater geochemistry was more successful than initially anticipated. Low-density sampling and mapping, as developed during the last 15 to 30 years for detecting large-scale geochemical processes at the Earth's surface, can also be applied to groundwater. Geochemical mapping at the continental scale permits cost-effective selection of scale and location of monitoring sites. To obtain a fully harmonized dataset at the European scale, high-quality measurements in a single laboratory are required and distillation of a strict quality control procedure. Comparison of the bottled water analytical results with those of water standards have shown that the majority of bottled mineral water brands fulfill the requirements of European legislation for mineral and drinking water. However, for some determinants, a few brands of bottled mineral water exceed the potable water standards. For example, the maximum values observed for aluminium, arsenic, barium, fluoride, manganese, nickel, NO2, NO3, selenium, and uranium. Comparison of bottled mineral water analytical results of the EuroGeoSurveys project with those displayed on bottle labels show a fairly good linear correlation, suggesting chemical stability of source aquifers over time, a necessary prerequisite of European legislation for bottled mineral water. The only drawback of this project is the uneven spatial distribution of bottled mineral water distillations, boreholes, wells. Finally, the new Atlas of the Geochemistry of Bottled Mineral Water is a valuable addition to the Geochemical Atlas of Europe series. The next few slides are for young or early career researchers. However, some of the information may be useful to experienced professionals. Question: why do we need harmonized geochemical baseline mapping for the present and future generations, and why the geochemistry of water and other natural materials are important to our quality of life? The answer is given with the following timeless statements from the Blue Book by Arthur J. Darley. Everything in and on the earth, mineral, animal, and vegetable, is made from naturally occurring chemical elements. The existence, quality, and survival of life depends upon the availability of elements in the correct proportions and combinations. On this slide, we see a plot of the mean concentration of chemical elements in the upper continental crust in brown color, European bottled water in blue color, and human blood in red color. As you can see, there is a very nice correlation among the three data sets. There are a few elements in bottled mineral water that do not follow the upper continental crust and human blood trend, and these are fluorine, chlorine, vanadium, iron, germanium, yttrium, cadmium, tin, lead, thorium, and uranium. What is a geochemical atlas? A geochemical atlas is a thematic special purpose atlas with maps describing the geographical distribution of chemical elements and other physicochemical parameters in different natural sample media such as stream water, surface water, groundwater, stream sediment, overbank or floodplain sediment, soil, rock, plant, etc. Why are geochemical atlases important? According to John F. Potter, geochemical atlases are of great importance because they provide data which can be statistically related to degenerative diseases of plants or animals and reflect variable levels of generated contamination or pollution. The importance of natural deficiencies or excesses of localized elements and their possible impacts on agriculture and humankind is particularly relevant. Hence, geochemical atlases should be useful to young and mature members of the Society of Environmental Geochemistry and Health, and not only. The EuroGeoSurveys Geochemistry Expert Group is dedicated to provide harmonized multi-purpose geochemical databases and has already published the Geochemical Atlas of Europe, the Atlas of Groundwater Geochemistry of Europe, and the Atlas of the Geochemistry of Agriculture and Grazing Land Soil. An important aspect is that all raw data and maps are freely available for downloading either through the internet or the DVD accompanying the publications. The Geochemical Atlas of Europe provides also the text. Advice to young researchers. When you design a geochemical project, it is important to verify the generated data by installing your own external quality control and assurance program. As you may have noticed, apart from verifying the quality of the bottled mineral water results, unexpected results were also checked. It is important to understand that your own external quality control and assurance program is completely different from the quality control procedure that the laboratory has installed to verify the generated analytical results. Before starting the processing of your project's analytical data, you should write a quality control report using both your own external quality control results and those of the laboratory. You must report all the encountered problems and solutions given. You must study, assimilate, listen, question, and criticize, and when you reach your final conclusion, you should be satisfied that you have investigated all possibilities. You must be open-minded, and when working in a team, you should not be afraid to propose a solution to a problem, even if you think it is far-fetched. You must be professional and follow a continuous development program in all your working life. There must be a balance in everything you do in all aspects of your life. Finally, my closing remarks. Production of harmonized strategic baseline geochemical databases and maps at the national and international levels is only possible if there is standardization of all procedures of sampling, sample preparation, chemical analysis, and data management. Without harmonization of methods and a strict quality control procedure, it is impossible to produce meaningful national and international level geochemical databases for multi-purpose use. Therefore, it is important for scientists working on the production of national and international geochemical databases to understand the concept of harmonization, standardization of methods, and to apply it in their work. Otherwise, valuable time, effort, and financial resources will be wasted in producing incompatible geochemical datasets both at the national and international levels. For the production of harmonized baseline geochemical databases and maps, consult the IUSS Manual of Standard Methods. Thank you for your attention, but I also have a few slides because this is a recorded video. Questions, comments, and answers. Question 1 and comment. Is there any attempt to compare this water geochemistry with the stream sediment and soil geochemistry rather than bedrock geochemistry? Geochemistry is affected by the lithology it goes through that is more related to the weather sediments. Answer. No attempt has been made to compare the bottled water geochemistry with that of stream sediment and soil. In Europe, the geochemistry of stream sediment and residual soil has been covered by the Forex Geochemical Atlas of Europe. And yes, the geochemistry of groundwater is affected by the lithology that the water is in contact with. Question 2. Do you have plans to measure in the next step organic ingredients in groundwater? Because in some parts of Poland we have a problem with underground waste dams, which can be sources of organic or persistent organic pollutants and very strange chemical compositions. Do you have any plans to expand your analysis for not only inorganic but also organic ingredients? Answer. There are no plans to analyze organic contaminants in groundwater. Please remember that the determination of the 72 parameters in the bottled mineral water samples was carried out by the German Geological Survey without any charges. We are aware that organic contaminants should be determined in groundwater, but for the moment there are no plans as the cost of repeating the same project and the determination of organic contaminants is very high. The fact that you have used bottled water as a proxy for groundwater geochemistry, one would hope that the bottling companies have actually cleaned up the water from any kind of organic contaminants before it reached the shelves. Theoretically, the bottling companies should not do any cleaning because the bottled mineral water is either natural spring or groundwater and bottled as source without any cleaning according to the existing European legislation. The sources of bottled mineral water are usually far away from any contaminating source. The bottling companies are obliged to submit the analytical results of groundwater to the relevant national authorities before they are given the license to bottle it. The chemical composition of bottled mineral water is monitored regularly, and according to European legislation, the chemical composition must be stable. There is no obligation nowadays to check the levels of microplastics and pharmaceuticals, and many producers of bottled and tap water, because it is expensive, do not check the level of other ingredients, and this would be a problem. Yes, it would be a problem if all potential contaminants are not checked. Tap water is different because all contaminants, including organic, should be checked. Next year, I will present you the tap water geochemical results that we have from the European countries. Question. Leaching of elements from bottled materials. Does it depend upon the glass and where the glass comes from? Answer. We have seen the most obvious, which is the leaching of chromium from green glass bottles. Regarding the source of colored glass bottles, one will have to do some detective work to find the source of the glass. We have not done this. Questions. Where do they come from? What's the commonality? What's the disparities? And there is a whole research to be done. Answer. Yes, you are quite right. We should know the source of the glass material, and yes, there is room for more research to be done. A comment. I like your end part, reminding people in terms of sample sizes, in terms of keep checking backgrounds, keep checking your references in terms of reference materials, something that is lacking in quite a lot of papers which are submitted for publication. Just those basic answers to good research are missing, and thank you for that particular reminder. Answer. Usually when I get such papers for review, I reject them immediately. Unfortunately, there are a lot of rubbish papers being published nowadays. Researchers must learn to validate the quality of their results, and they should learn to write up a quality control report. Comment question. I'm actually quite interested in the entirety of the presentation and going to the early slides in terms of overexploitation and over-extraction. There is a question, if this continues to occur, is there the possibility that whatever inorganics you are seeing in there, can they become over-concentrated? Is that possible, or is that a stupid thing to say? Answer. Remember that the chemical elements in the aquifers are sort of diluted in a large volume of water. So if there is over-exploitation and over-extraction, yes, it is possible to cause their overconcentration in the remaining smaller volume of water. I'm worried about the Sahara because if they start tapping the groundwater as they do in Saudi Arabia, then this danger that you are saying, it could happen much faster because the groundwater in these desert areas is not replenished as in temperate climates.